Differential equations. You know, they're the language of the universe, describing everything from a swinging pendulum to how electricity zips through a circuit. But let's be honest, solving them can be a total mess, a real deep dive into some pretty gnarly calculus. But what if there was a shortcut? What if you could turn all that chaos into simple, clean algebra? Well, today, that's exactly what we're going to do by exploring an incredible tool, the Laplace transform.
So here's our game plan. First, we're going to wrap our heads around the core idea, this whole calculus to algebra translator concept. Then, we'll actually build a piece of it ourselves to see how it works. After that, we'll see how it scales up, and finally, we'll use a simple 3-step blueprint to tackle a real problem. Let's jump in.
All right, so the big challenge in so many areas of science and engineering is solving what are called initial value problems. Basically, they're differential equations that have a specific starting point. And trust me, they can get complicated, and they can get complicated fast. We need a better, more elegant way to handle them.
I mean, really think about that question. What if you could solve a calculus problem using just algebra? This isn't just a hypothetical. That's exactly what the Laplace transform does. It's like a universal translator for math. It takes a really tough calculus problem from its native language, let's call it the T world, and translates it into a much, much simpler algebra problem in a new language, the S world. You solve it there with tools you already know, and then you just translate the answer back. It's brilliant.
So how does this magic translator actually work? Well, to really get it, we're going to pop the hood and build the most important piece from scratch, the transform of a derivative. This little piece of machinery is the key that unlocks this entire process. Okay, so it all kicks off with the formal definition, which, yeah, it looks like a pretty intimidating integral. But here's the thing. To crack it open, we use a classic trick from our calculus toolbox, integration by parts. This lets us break the problem down into pieces we can actually work with. And this is where that trick really pays off. After we rearrange the pieces, look closely at what just pops out on the right-hand side. Would you look at that? It's the Laplace transform of our original function. It was hiding inside the equation the whole time, just waiting for us to find it. And this brings us to the grand finale. The transform of a derivative, that messy calculus operation, becomes simple multiplication and subtraction in the S world. It's just S times f of s minus the initial condition. We literally just turned calculus into algebra. That is the magic right there. This is why it's such a secret weapon in things like control systems and circuit analysis. So, that's amazing for the first derivative. But what about the really messy stuff? Second derivatives, third derivatives, the higher order problems. Well, it turns out there's a really beautiful and predictable pattern that emerges. Okay, take a look. On the left, we've got a result for the first derivative. On the right, we have the transform for the second derivative. Do you see it? For the second derivative, we get s squared times f of s, and then we subtract off terms for the initial conditions. That pattern of multiplying by s just keeps on going. It's so cool. And this predictable behavior leads us to this powerful general theorem. Now, I know this formula looks like a monster, but don't let it intimidate you. It's just a pattern we literally just discovered, but written down in a formal way that works for any derivative, the nth derivative. This is our power tool. It gives us a rule to turn any derivative, no matter how complex, into pure algebra. Okay, so we've got this incredible power tool that can turn calculus into algebra. Awesome. But how do we actually use it to solve a problem? Well, the great news is it all comes down to a simple, repeatable 3-step blueprint. And here it is. It's this simple. Step 1. Transform. You take your entire messy differential equation and you zap it from the T world over to the S world. Step 2. Solve. Now you're in the algebra world, so you just solve for your function, y of s, using basic algebra. No more calculus. Step 3. Invert. You take that clean algebraic answer and use the inverse transform to bring it back to the T world. That's your final solution. Transform, solve, invert. That's the mantra. All right, now for the really fun part. Let's put our blueprint to the test. We're going to take a real initial value problem and watch the calculus literally just melt away. So here's our problem. We're going to hit every single piece of it with the Laplace transform. The derivative, dy over dt, bam, that becomes sy of s minus y of 0. The 3y term, that just becomes 3y of s. And that 13 sine of 2t on the other side, it has its own known transform we can just look up in a table. And just like that, poof, the calculus is gone, it's all algebra now.
See? Now we're on easy street. The heavy lifting is over. We plug in our given initial condition, y of 0 is 6, and from here on out, it's just rearranging terms to get y of s all by itself. We're just factoring and dividing. This is the kind of algebra you're used to. This is our solution, but it's just in the S world for now.
And for the final step, we translate our answer back home. We take the inverse Laplace transform of y of s. Now, to do this, we often need a method called partial fraction decomposition, which sounds super fancy, but all it really means is we're breaking our big, complicated fraction into smaller, simpler pieces we can easily find in an inverse transform table. Once it's broken down, we find the inverse for each little piece, put them all back together, and there it is, our final answer, y of t. Problem solved.
And that, right there, is the beautiful symmetry of this whole thing. You take a really complex problem, you translate it into a world where it becomes simple. You solve it there with familiar tools, and then you translate that simple answer back into the solution you were looking for all along.
It really makes you think, doesn't it? We just used a mathematical tool to completely change our perspective, to make a problem that seemed impossible suddenly manageable. And it just begs the question, what other chaotic systems out there, in engineering, in finance, maybe even in biology, are just waiting for the right language, the right transformation to turn them from chaos into an elegant, solvable puzzle?